Hello, hello, hello. So we are back. We yesterday covered the generics and all. Now today we'll be covering scoping rules. So let's get started. Scoping rules. So scope plays an important part in ownership, borrowing, and lifetime. That is, they indicate to the compiler when borrows are valid, when resources can be freed, and when variables are created or destroyed. So we know that. We know this function because of these curly brackets. This is the scope. Outside of this, well, if you don't return it, this is not going to get carried away. And now for main function, this is the scope, sort of a big one, isn't it? Yeah. This is for loops scope, like this small one. And this is just the scope nested in main function. So yeah. So we know curly brackets and whatever in between them is a scope. All right. So RAII. Now variables in Rust do more than just hold data in the stack. They also own resources. Example is box T, which is storing a pointer, owns memory in the heap. Rust enforces RAII, which is resource acquisition is initialization. So whenever an object goes out of scope, its destructor is called and its own resources are freed. So this is RAI. Resource acquisition is initialization. RAII, all right, is a programming idiom used in several object-oriented statically typed programming language to describe a particular language behavior. And in RAII, holding a resources is class invariant and is tied to object lifetime. Resources allocation or acquisition is done during object creation, specifically initialization by the constructor, while resources deallocation or release is done during the object destruction, specifically finalization. So by destructor, in other words, the resources acquisition must succeed for initialization to succeed. Thus, the resource is guaranteed to be held between when initialization finishes and finalization starts, which is holding the resources is class invariant, and to be held only when the object is alive. So thus there are no leaks and there are no resource leaks. RAI is associated most prominently with C++ when it originated, but also Ada, Vala. Oh, these are also languages. Well, I've never heard of them, but they exist. And Rust. Well, we are learning Rust. Now, the technique was developed by exception safe resource management in C++ during 1984 to 1989 in 5 years, primarily by Bejarne Strostrup and Andrew Goy. What is this name? Goynik. All right. So there are other idioms included like constructor acquire, destructor release. All right. So CADRE. So this is also the same RAII. And one particular style is used called scope-based resource management, which is SBRM. Now this latter term is used for special cases of automatic variables. Automatic variable is something that is in computer programming. An automatic variable is a local variable which allocates and deallocates automatically when program flow enters and leaves the variable's scope. Now, the scope is lexical context, is the lexical context, particularly the function or block in which variable is defined. Local data is invisible. All right. RAII resources to object lifetime, which RAII ties resources to object lifetime, which may not coincide with the entry or entry and exit of a scope. Notably, the variable allocates on the free store have a lifetime unrelated to given scope. However, using RAII for automatic variable, which is SBRM, is most common use case. So we've seen it. Let's move on. All right. There are limitations also. What are the limitations? RAI only works for resource acquired and released, which is directly or indirectly by stack allocated objects. When there is a well-defined static object lifetime, all right. So if there is a static object lifetime, well defined, then only this RAI works for resource acquisition and release by stack allocated object. So heap allocated object which themselves acquire and release resources are common in many languages, including C++. Now RAI depends on heap-based objects to be implicitly or explicitly deleted along all possible execution paths. In order to trigger its resources releasing destructure or equivalent, this can be achieved using smart pointers to manage all heap objects, with weak pointers for cyclically referenced objects. Well, someone claimed that the use of RAI can cause memory fragmentation, which in turn can cause cache misses and 100 times or worse hit on performance. Oh, so this can be worse hit on performance. All right, we have a better idea of what RAII is. So Rust enforces RAII, which is resource acquisition is initialization. So whenever an object goes out of scope, its destructor is called, and its own resources are freed. Now this behavior shields against the resource leaks bugs. So you'll never have to manually free memory or worry about memory leaks again. Here is a quick showcase. Now this is the selling point of Rust, I guess. This is there in C++ also, but oh yeah, I think this is very automatic. Like you allocate a variable, you don't have to free it, and I've never used a malloc or something like that in Rust uh, till now. All right, so let's see how that works. Because to write a string, you have to allocate a memory using an array or something like that, or just using malloc. You have to write something implementation of it. But over here, we just use string types, vector types, and all these pointers types. But we have never used the malloc or any other method used for allocation of memory in Rust right now. So we don't have much of idea, but I think it gets automatically allocated a memory and automatically it's freed because there is a concept of ownership and borrowing. So as soon as the owner, is out of scope or, out of its lifetime, the allocated memory, which is, allocated automatically, gets freed automatically using Rust. All right. That's what I think for now. Now this is a RAII.rs program. We have to run it. So we'll first get into our project directory. Inside that Rust, and over here we'll create RAII.rs and we'll paste this. But first of all, let's read it through. So there is a create box function in which we have a let unused variable box1. Therefore, we have used underscore. So let box1 is equals to, we have a box which has a pointer, and new is what? We have a 3 which is of type i32. So there's a pointer which is pointing towards 3 which is of type i32. Now allocate an integer on the heap. So it automatically allocates integer on heap. That's what Rust do. In C++ or C, I guess we'd have to do something like that manually. In C we had to, but in C++, since I've never used it, I don't know. Now the box 1 is destroyed here and memory gets freed because this will go out of scope sooner or later. So it gets freed over here since it is not getting used. And then what happens is we have a main function. Inside that we have again box 2, same thing, just a different number, that is 5. So there's a pointer pointing towards 5, type I32. And inside main we have a nested sort of scope which has a box 3, same, just the number is different. So box 2 exists over here also because that's the rule in nested scopes. Now what happens is box 3 gets allocated over here in this scope. And as soon as this scope is going to end and we have used box 3, it is destroyed over here and memory gets freed for box 3. Now what it is saying is creating lots of boxes just for fun. Well, we are, how many? Well, we are doing in the range of 0 to 1000, which is 1001 boxes for now. There's no need to manually free the memory, and I don't think there is a need to manually allocate the memory also. So both are the plus points. They automatically gets created, and as soon as they get created, they get destroyed in this loop because they are not getting used. All right, and box 2 is destroyed here, and memory gets freed because box 2 is also near going out of scope, so it also gets freed. All right, so yesterday we downloaded what, Valgrind. So first of all, we'll use Rust C to compile the rai.rs, and then we'll run it. First of all, rai, and it runs, but we want to use Valgrind to see any sort of memory leak and all that. Valgrind and rai. So it is doing that. So heap summary is that in use at 456 bytes in one block, and total heap usage was around, why 1011? Because 1001 was used in for loops, and then there were, I guess, three more that I can think of. Or not this. I want to upload. So over here, this might have created about 1001 1001 allocations and reallocations simultaneously. Over here it created one allocation, so 1002. This is 1003, this is 1004. As for others, I can't think of others, but creating main functions and all that, which we are not doing but is happening automatically, might be also responsible for that. So I think that's why we are seeing something like this, where we have 1011 allocs and 1010 freeze. One did not because, well, it might have been static, and it is saying 6540 bytes were allocated. Leak summary is 0 bytes lost in 0 blocks, so no loss. Indirect lost is also 0. Possibly lost is also 0. As for still reachable, what is this? I don't know, but still reachable is 456 bytes in 1 blocks. All right, suppressed is also 0. So if you want to, check again, so you can run it with this leak check full. Well, we can do that. Should we do it over here or before that? I think over here. Low leak check. Full. Still the same. All right. So I think it is working. Well, what I want to do right now is just create a normal main function and just try doing what we were doing. But main.rs. we'll just create a main function, and that's all we compile, and we will see how many allocations and deallocations were there. All right. We'll create rust c and main.rs. No output from main because that's what we did. Now valgrind and main.rs. See, so only creating main function was 9 allocs and 8 frees. So now I can think of why there were 1001 allocs, because 9 just came out of main. So if we count it till 3 that and 1001, so 1004, then adding 9 to it, well, we have 13, but here it's only 1011. Not much of an idea right now. But yeah, only creating just normal functions can be heavy. No, I'm doing some sort of mistake. Let's count it again. So create box is calling this function, all right, which is allocating this memory once at a time. So this will create only 1001 because of this. So we don't need to count this. 1001 allocated from our side, 1002 because of this, 1003 because of this. So we have only done 1003. And if we think like main gave us 9 allocs more, so now it adds up to nearly about 1012. 9, 3, 12, yeah, 9, 10, 11, 12, exactly. But we had 1011 allocations. So what is the one that I'm adding more? I don't know. So let's go to main.rs and change something. Change what? We'll change something like uh, fn, and we'll create, let's say c is a function we are creating a demo function. There shouldn't be much of a problem. Just a warning that we are not using that c function. Yeah, a warning is there. And algorand main, just 9 allocs. That's what I expected. Because what about if I use it with this? How would I call just c like a function? That's it. Now if I try running valgrind, still only 9 allocs. So I think both are same. Doesn't matter how many empty functions you create, you still have to do 9 allocations. All right. So I get your point. Valgrind gave us something like this. Yeah, 1013 allocations over here, where we only got 1012 or 11 allocations from rai.rs. Where is this? Yeah, we only got 1011. I don't know why. It's missing one. So no leaks here, and we found also no leaks here. Good for us. Well, this is different from what we are getting. Yeah, isn't it? It's different. So I guess there is a leak. Or there is not. Let's ask someone. Let's ask GPT or something like that. Is there a leak in my program. Till then, I'll take a short break. Hello. Yeah. So we are back. And I think why this is happening is I think we might have a different version of Valgrind and all that. Whereas this documentation had a different version of Valgrind. So that's what I can think of right now. Uh, let's try just doing Valgrind and nothing else. But it still gives us the same thing that we are getting, isn't it? Yeah, it gives us the same thing. So I think it is because this is a different version of Valgrind, whereas ours is different. So this AI says, no, there are no memory leaks. Your Valgrind output looks clean. Here's a breakdown. So definitely lost is 0 bytes. Indirectly is 0 bytes. Possibly is also 0 bytes. Errors 0. The 456 bytes still reachable is not a leak. This is a memory that still had a valid pointer to it when the program exited. Typically the Rust runtime and standard library internals. That's what I think of. It was intentional, not freed before exit. It was intentionally not freed before exit, which is normal and harmless. Now, this is exactly the behavior Rust RAII system guarantees. Your own resources were properly cleaned up when they went out of scope. Okay. Now, destructor. So there is a destructor, which is this. So first of all, let's read the theory. So the notion of a destructor in Rust is provided through a drop trait. All right. Now the destructor is called when the resources goes out of scope. This trait is not required to be implemented by every type. Only implement it for your type if you require its own destructor logic. Run the below example to see how the drop trait works. Where we'll learn this drop trait. All right. So in a standard, so this is how drop trait has been defined, like a publicly trait which is called drop. Inside that we have a drop function which takes a mutable self of itself, and that's it, I guess. That drops everything and anything. But it is taking reference, no, it is not taking self, but that is taking mutable reference. All right, so it can change it to something like zero or null, something like that. We now know drop trait is how is it defined, all that. So when the variable in the main function goes out of scope, the custom destructor will be invoked. So there is a custom destructor over here, which is we have created structure to drop instead of just drop. And we are implementing drop for to drop. And we are defining the function again. We are saying mutable self. We are taking a reference of mutable self. We can change the reference. That's what it means. Now we are printing to drop is being dropped, and that drops it. Now there is a x is equals to 2 drop. All right. Now we are printing made a 2 drop, and like x is assigned the value of 2 drop, which is a structure in itself, and we are dropping. Like, what is happening right now? Can somebody explain this to me? So it says made a 2 drop, and then x is dropped where? X is dropped somewhere here. All right. So that's why it is saying 2 drop. And why did we use x as 2 drop? What if this? Instead, how about this? All right. So what I think to drop is just a print statement, uh, which gets printed when the X gets dropped. That's what I can think of right now. But let's still sort of, clarify what it means. Clearly explain this program to me. Let me read it. So this program demonstrates the Rust's drop rate and how destructor destructors work. Now here's what happens step by step. So there's a structure we have defined as toDrop. It creates an empty structure called toDrop that doesn't hold any data. Yeah, we know that. Now we have an implementation of toDrop. So we are implementing drop trait for toDrop. So drop trait has been implemented for toDrop, and inside that we have a drop function. Inside that, whenever it's getting dropped, uh, before getting dropped, we are first of all giving it a print statement that it is being dropped. So be careful. So this implements a custom destructor for toDrop. The drop method is automatically called when a toDrop variable goes out of scope. Think of it like a cleanup function, but when it gets cleaned up, it will screams out loud or prints out loud. The toDrop is being dropped. All right. Our main function is looking something like this exactly, creating X as toDrop, and as soon as X goes out of scope, it first of all prints that I'm going out of scope or toDrop is being dropped, and that's it. Println, we made a drop, and so there is an execution flow. So first of all, there is a X which is equals to the structure toDrop. So creates an instance of toDrop. Then we have a print statement where we are saying made toDrop. So it prints to the console. Now as the end of main over here, the variable X goes out of scope. So Rust automatically calls the X.drop. And the fourth step, we print the toDrop is being dropped, because that's what we implemented for drop, our custom drop. Key takeaway is Rust automatically calls the drop function, this function, drop function, when a variable leaves the scope, ensuring resources are cleaned up without manual intervention. Now, this is our AII principle. Okay, all right. Ownership and moves. All right. So this is our third topic, I guess. Subtopic. No, only second one. Oh, the first one was scoping rules. Inside that, we have two subtopics, and they have also two subtopics. So, well, that's why I said this is going to be, extensive, because lifetimes is like has 9 topics in itself. So this will not be able to, I will not be able to cover it today only. So, all right. Now, ownership and moves. Now, because variables are in charge of freeing their own resources, resources can only have one owner. This prevents the resources from being freed more than once. Note that all variable own resources, like references, let's, close all these tabs, phantom data and all that. Now, pointers and reference. In which chapter are we seeing this? Because this isn't rest by example. So which chapter? It is 8th. We've seen it. We've seen this pointer and reference. So no need to see this again. As for some dramatic printing. So here we were, learning about references and destructuring those references. Yeah, I remember that. Mm-hmm. All right. Ownership and moves. So when doing the assignment of let x is equals to y, or passing function arguments by value like foo and x, we are giving it a value of x. Foo is the function. The ownership of the resources is transferred. In Rust speak, this is known as move. After moving resources, the previous owner can no longer be used. This avoids creating dangling pointers. Yeah, we know that somewhat. Now we have only two functions. First is destroy box, which takes the C which will be a pointer, which is box I32 of type I32 inside that. And then we have a print statement saying that destroying a box that contains, you know, C. We print that C and then C gets destroyed over here because we are not taking a reference to the pointer. We are just taking that pointer with this destroy box function. So whenever we give any sort of pointer to this destroy box, it destroys that. Because Rust automatically runs the, drop function as soon as the C goes out of the scope. So the function gets dropped and the previous owner cannot be called, obviously, because we have sent its data to this function. So let's see how we do that. So we have X, which is 5 of type U32. So this is a stack allocated integer. Now we are copying X into Y. So no resources are moved because, well, numbers get copied. That's what we know. So let Y is equals to X. So it has been copied. Nothing has moved. No reference, no borrowing. Over here, we are printing it. So it says both values can be independently used. X is not dependent on Y, Y is not dependent on X. So yeah, independently moved. Used. Let's try printing it. And then we have A is a pointer to heap allocated integer. Now A is a pointer towards 5 I32. So we created something like 5 I32 and we created a pointer towards it. And that pointer has been, allocated to this A variable. Is it called allocated? It's called assigned. All right. So we have assigned the pointer from here into the A variable. Now we are printing the A. All right. Now we are moving that A into B. So this 5 gets moved into B. The pointer to 5 gets moved into B. So now A becomes sort of invalid because moving happens. Move A into B. So that's what we did. We assigned A's value to the B. The pointer address of A is copied, not the data, into B. The pointer address of A is copied into B, not the data. So data has been moved because of the ownership, I guess. Now both are now pointer to the same heap allocated data, but B now owns it and A sort of becomes invalid. And error. See, we see an error that A can no longer access the data because it no longer owns the heap memory. So as soon as we try printing A after assigning its value to B, we'll get an error. All right, it says try uncommenting this. We know we'll get an error. But still, we'll do that. And then we use destroy box function on B, and then B also the pointer gets destroyed because that's what it does. It drops the value as soon as this destroy box function runs totally after printing a statement. We destroy the B. Since the heap memory has been freed at this point, this action would result in dereferencing the freed memory, and it is forbidden by the compiler. So yeah, if we try printing B again, since it has been freed, we'll get an error. So it says error, same reason as the previous error, exactly. Because now previously A didn't own the data and it got invalid because everything got copied to B. Not everything, but the pointer address got copied to B, not the data. And over here, the B was passed into destroy box, which gets freed afterwards. After printing this statement, it gets dropped or destroyed or freed. So yeah, now we can't even access B. So let's see all these errors, but before that, let's print our statements. So X is a 5 and Y is a 5. A contains 5, and that's what we did over here, where X is a 5, Y is a 5. All right. Then over here, X contains 5 because of this pointer towards it. Now we are destroying a box because of this. over here. We're destroying B. All right, so we know what we printed, and now we want to see some errors. So let's see some errors and move on. We get an error because of this, because A has been assigned to B and it can no longer be, accessed because it doesn't own that data now. So we get something like borrow of a moved value A. We are trying to borrow something that has been moved. It says because A has a type box I32 which does not implement the copy trait, so it gets moved. So value has been moved here. But why X and Y were copied? All right, they were not moved, so they can be used independently. Uh, See, X can be accessed from here. X is getting accessed from here after assigning its value to Y, because that's a number. They are not pointers. Pointer gets moved. Pointer gets gets ownership and all that. Numbers can be directly copied because that's easy thing. Now print statement is something like value borrowed here after move. Exactly. So we are trying to borrow A when it has been moved to B. This cannot happen. We can do A dot clone. We know about that, but that's not what we want really. We just want to see this error happening in real time. Now what about, well, let's run it normally and then we'll see the error for B. Now let's see the error for B because it has been destroyed over here. In, as soon as it gets out of the scope, it gets destroyed. Exactly, see? It says we can use B clone, we can pass B's clone, then B's clone will be destroyed, but that's not what we want to achieve. We want to destroy the B. All right, since we know what this function does, ownership and moves, we shall get moving on. Now in ownership and moves, we have a mutability and partial move. So this is mutability, and after that we have partial move. Partial move is somewhat bigger than mutability. So let's get back to mutability. Now see what the mutability is. So mutability of data can be changed when ownership is transferred. So there's a function main and we have a let immutable box is, box, and we have a pointer towards 5. So 5 is, number type U32. We have a pointer towards this 5, which is getting assigned to this immutable box variable. Now we are trying to print this immutable box, which will print 5. No worries about that. And exactly, it prints 5. Then we have a let mutable box. So we created mutable box using this keyword mute. All right, and we are assigning the immutable box over here. So the pointer from immutable box get assigned to a mutable box. Then we are trying to print the mutable box. That's what we did, and it prints that mutable box contains 5. And then we made a change to mutable box because it can be changed. Immutable cannot be changed, mutable can be changed. We know about that. So after changing the box's value or the mutability box's value to 4, now this pointer will go to 5. It will erase this, it will create a 4, and we get a 4. So we try to print it, we get a 4. Now here's the error it wants me to show you, is that if you try to change the immutable box, we are going to the reference of it. We are going to the, we are dereferencing that pointer going towards 5. We are accessing the 5 and removing that 5 as a value of 4. So we give it a new value of 4. Then the same pointer is 4. We don't create a new pointer for it. We just give it a new value. That's what it does. But since it's immutable, we can't do that. But if it was mutable, we could. So let's see the error. It says something like, cannot assign an immutable box as an immutable box is not declared as mutable. Well, obviously. And see, this name is confusing because it is saying immutable box, but we are using it as mutable. So yeah, but that's for just for example. You can change it to A, B, C, D, but it's trying to tell us that this is an immutable box. Do not try to, change it or mutate it, because that will give us an error. Mutate is like changing the value. So it says cannot assign a 4 to this immutable box. It is also helping me by saying that try adding mute variable, but that will make this immutable box a mutable box, because that's what we did over here. All right, so I guess we know mutability. We shall move on. Partial moves is there. Partial move is something we've known. Why? Because of ChatGPT. We have other courses too. So over there, we were following instructions of ChatGPT and learning theories. So we know about a little bit about partial move, but let's see what it has to tell us. So partial move is something like within the destructuring. I think we have studied destructuring, or we have not. We have seen destructuring. We have destructured tuples, array and slices, enums, pointers, and structures. So we know destructuring. So it says within the destructuring of a single variable, both by move and by reference pattern bindings can be used at the same time. Now doing this will result in a partial move of the variable, which means that a part of variable will be moved while other part stays. In such a case, the parent variable cannot be used afterward as a whole. However, the parts that are only referenced and are not moved can still be used. Note that the type that implements the drop trait cannot be partially moved from, because it is drop method will use it afterwards as a whole. In this example, we store age. All right, we'll see first of all. We have a main, we have a derived debug so that we can print this structure with a question mark. Where is it? Over here, question mark and colon. This will give us some sort of error, not because of this question mark, but because of how we are using it. All right. And then we have a structure of person, which stores name and age. Name is a string and age is a box. U8, I don't know why box. We should have just taken it as number. All right. But since we have a box, and if we try to use this name, which is a string, which is a pointer, somewhere else, so this person structure does not gets moved. Only the name is getting partially moved. This person structure remains intact, and as soon as we release this name pointer from wherever we were using, we get back a normal person. So let's see what's happening right now. So it says error, but we are not reading this. First of all, we'll see how this function works, how this main function is getting implemented. So let there be person with a name which is Alice and age of 20. Yeah, I've seen this example, but in that example, our age was exactly 20, not a pointer, which is box new 20, not like that. And then let person, we are dereferencing the person over here. So let person, a big person, we are dereferencing it by name and age, and we are taking a reference of age, not just taking the age, we are taking the reference of age. But name is partially moved to this person. So as soon as we say print the age, it prints the reference of the age. As soon as we say print name, it prints the, name, not a reference. And if we try to, access this data, which has been assigned or destructured over here, if we try to access this person data's sort of age, we should not get any error. But if we do that for a name or the whole person structure, we should see some errors. So no errors right now. Why? Because we were destructuring this person, small p person, which is this, by taking a reference of age, not the whole age. We were just taking the reference. As for name, we were taking the whole name, like the whole pointer for that name. So that name pointer has been partially moved to this bigger person, big P person. So that's what's happening right now. So we have age, which is 20. All right. Yeah. We have a name, which is Alice, because of this person. And then we are saying person not age, which is we are trying to access this. We can access this because this has not moved. We are only taking a reference of this. So this is still there. We can access this. As soon as we do something like person instead of age, we say name, which has been moved to this bigger person. We get an error. See, we get an error. That value is moved from here and to here. See, over here. If we just take a reference of it, then it will not be moved and we can print it easily. And then we can also, sort of print this person also, this whole data set person, because we are not doing anything illegal right now. We are just taking a reference. Reference is something like, I guess, ampersand. I guess this is reference. Can we do this? Or do we have to say reference? We see an error. Expected identifier. All right. So we are taking, sort of dereferencing it. So we'll have to say reference. We are taking a reference of it. We are not passing it by reference. We are taking the reference. All right. So this is what we expected. But as soon as I remove this reference from the name, so now this name from this smaller person gets destructured and moved to this bigger person. Now we can't access this whole, smaller person again. Why? Because the name, which was a value inside this, has been moved to this bigger person. As for age, it has been just taken a reference of. So this has not moved, but we'll get an error because of this name. And yeah, this is what we expected. It says add a reference or just don't use it. All right. Now we get that there's some problem. Now let's just take the reference to it if you want to. But now this is not partial move. But as soon as we remove this reference, that becomes a partial move because name out of this person, the name gets moved, whereas the age does not. So that's partial, like half. All right. Not exactly half, not 1/2, 1/2, but fractional. Something is moved, something is not, like that. Now let's see what this error is. It says cannot move out of the type which implements the drop rate. So it says implementing drop for person. This is a structure. We are implementing drop for that function for the person, and we define the drop rate as print this as soon as print this for the self. You're taking the mutable self. So as soon as this person goes out of scope, well, it gets dropped and we print this. So we'll get a very, very timing error because over here it gets, I guess, destroyed. It does not. So it gets destroyed over here. Here. After this gets totally utilized. Cannot move out of the type which implements drop rate. I don't know what that means right now. Can someone please explain me? Let me read. And this code demonstrates the partial move in Rust, why they are problematic, and with type that implements drop. What's happening is the person structure contains, a name, age, which is a name is a string, which is heap allocated. Age is a heap allocated wrapper because you ate or I ate. Well, they can just exist as it is. No need for pointers and all. But over here, we are giving it a pointer. Yeah, it has a weight. And I guess what this A is sort of their lifetime. So their lifetime is this A. Now, second thing that's happening is drop rate implementation means the Rust will automatically clean up function with when the person goes out of scope. So person goes out of scope here. All right. But if we set something like, if we define something like person in a scope, that would create issue for us. Like this would give us a error. This should give us an error. Yeah. So it gives us an error. If we don't just use these, yeah, we see that person is getting dropped over here, isn't it? Person gets dropped over here. So let's first of all comment all of this out, and after this, let's try printing something like print ln hi. Hi. So first of all, it will get dropped. Then we see hi. So that's why this will not work as soon as we try, dereferencing this person, but it does not exist outside. It's outside of this scope because that's getting dropped. That's what I understand, but I don't understand what is the problem. Like, why would someone, do something like that? Like explaining that in a scope and then dereferencing it out of the scope. Like without even implementing this would have happened automatically. So I don't know why. Is it just like they are trying to tell us that this is what happens or something like that? Uh, But let's read this. So drop trait implements mean Rust will automatically call cleanup function when person goes out of scope. We know that. Now destructuring line like let person and ref name, ref age is equals to person uses reference for both field, which means that both name and age are borrowed, referenced, not moved. Yeah, over here, we are taking a reference of it. We are not moving it. Let's move it right now. So this is now moved. Hmm. So we had an error because of this semicolon that we did not use. And now we are getting because of this. And now we are getting because of this. AGE. All right, all right. Let's do everything. And this should work. This works. Then this works. Now try uncommenting this. We'll try that. Sorry. First of all, uncomment this, then run. We should get an error. That's what it says. Yeah, exactly. So this is what's happening right now. Since we were taking a reference of it, we didn't see much of an error because of this implementation. But now we are seeing the error because we cannot destructure it like this after that. Because as soon as this tries destructuring this, means this person goes out of scope, and as soon as this person gets out of scope, uh, well, drop takes the self, a mutable self, and destroys everything. So it cannot be dereferenced, I guess. It can be taken a reference of, and then we can destructure it. But you can do this, but not just move the value from this person to here, because that will create some problem. We can do partial move now. Yeah, see this? So it says the destructuring line where the let person name reference person uses reference for both field, which means both name and age are borrowed reference, not moved. This creates a partial moved situation. This also creates a partial moved situation. Like we are taking a reference of it. So this is also partial moved. I don't think so. I don't think so. So I don't think this is very smart. So what I can think of is whatever I've told. As for let's read this last one, which says in this example, we store the age variable As soon as we drop this implementation, everything works fine. Everything goes back to normal. And we are also accessing the person's age. So this is now not a partial move. Or is it? Well, it is partial move because now we are not taking it by reference. But if we took it by reference, then it shouldn't be a partial move. That's what I'm trying to say. So in this example, we store the age variable on the heap to illustrate the partial move. Now deleting the reference in the above code would give an error as the ownership of person not age would be moved to the variable age over here. All right. If person not age was stored on stack, the reference would not be required as the definition of age would copy the data from the person not age without moving it. Like if it was just 20, then no need for this reference. It'll just be copied. What happened? Person is defined as box U8. So let's do that. Let's tell it that this is just U8. Right. Now no errors should be there. Exactly. But this is still partial move because name is a string. So we take it by reference and now this shouldn't be partial move and everything should work fine. All right. See, it works fine. Because age gets copied without even moving it. That's why we didn't take age as just a number. We took it as some sort of pointer that we have to manage and all that. All right, so let's move on. Now, ownership and moves is done. The partial move and mutability is done. Now we are at borrowing. Inside that, we have mutability, aliasing, and the ref pattern. So let's do this. Now borrowing. So most of the times we'd like to access data without taking ownership over it. To accomplish this, the Rust uses a borrowing mechanism. Instead of passing object by value t, objects can be passed by reference %t. Well, I'm bored of these theories, but this is important. I'm still bored. So let's try finishing it. Then, because this lifetime is damn too much. Static, coercion, illusion, bonds, bounds, traits, structs, methods, function, explicit annotations. So lifetime of all these. Borrowing. So most of the times we'd like to access data without taking ownership over it. To accomplish this, Rust uses a borrowing mechanism instead of passing object by value t. Objects can be passed with a reference t. Now the compiler statistically guarantees via borrow checker that reference always points to a valid object. Now that is why references to an object exists. That is while the references to an object exist. Object cannot be destroyed. Now this function takes the ownership of a box and destroys it. We have a function eat box i32, which is taking a box i32, which is of type box i32. And we are printing that destroying the box that contains this box i32 because yeah, we are not taking a reference to it. We are just taking the box, the pointer. So the ownership gets transferred to this function and this does not use it. And as soon as this function goes out of scope, the pointer gets dropped automatically. Now this function borrows an i32. So instead of taking, the whole pointer, it just takes the reference of the pointer. This borrows it, so it will give it back. Or it will not do anything. This is not a mutable borrow. What if it took a mutable borrow? We'll see that also. So we have a let boxed i32 is box 5. Stacked i32 is 6, which is defined in stack. So there is no pointer to it. It is just there. We can copy it, but for this we have to move it. Now we are sending both of them, I guess, to borrow I32, which takes a reference of it. So we are sending both of these numbers by reference. I think no problem till here. Now we create a inner scope which says let reference to I32, which is a unused variable of type, reference of I32 is equals to boxed I32. Can we do this? Well, this is not just a reference of I32. This is something like, uh, you know, pointer that has I32. So that's a different level of complexity. So we take a reference to that data contains inside the box, and then what we are doing is eat box I32 is like we are sending this eat box function inside over here. So boxed I32, which was there outside, gets destroyed in this inner scope. So this will not live outside of this box. So this is why we are getting the error. We eat the boxed item, which is boxed I32. And then we do what? We borrow the I32, which is, try to reference this RAM thing again. We cannot do that. We cannot do that. See, where is it saying, destroying the box that contains 5 over here? So, you know, as soon as we say something like print high, high, we'll see. So it is getting destroyed exactly over here, not going out of scope, like not over here, because that then we would see something like high. So that's not what's happening right now. So it tells us to just comment it out and everything will work fine. We'll do that. We'll just comment this out and everything works as it should. And where are we destroying this box? Over here. How do we know that? Because this will say print high first and then we'll see this destroy and all that. High. After high, we'll see destroying box. No, before. Oh, sorry. Over here, it's eat boxed. Oh, sorry. I sometimes forget that. So, yeah, this is eating the boxed item. Now, over here, it tried borrowing it. It can, because this is not getting out of scope. Now, as soon as this inner scope ends, this reference to I32 gets ended, and whatever we borrowed, well, gets nullified because it has been dropped. And then we try to just eat the box. All right. And what else I know is, since it is taking a reference to box I32, before taking a reference, we cannot just eat this box I32. If we do that, we cannot take this reference. Uh, why is that important? Because sometimes we do that in C or C++. That's why what I've heard is sometimes we do things that are stupid. That's why Rust won't allow us to do that. So this is borrowing. Let's move on. We have a mutability. Did I leave something in borrowing? I don't think so. So these are just instructions that we know that what we are doing. So just lots of comments. Mutability. So it says allow dead code, allow clone and copy, or derive clone and copy for what? For this structure that is blue. And it has a static string. So this is this has a lifetime of the whole program. So this gets compiled to binary. What this means is till the program lives, this variable is not going anywhere. This variable also lives. That's what it means. Static string. The mutable data can be mutably borrowed using ampersand mute t. Now this is called mutable reference and gives a read or write access to the borrower. In contrast to the ampersand t borrows the data via immutable reference and the borrower can read the data but not modify it. Okay. Yeah, I was telling I was forgetting something. This is what I was forgetting. Like instead of borrowing, how about I take a mutable borrow of it? Now what happens? Oh, first of all, remove this line. Now what happens? Still we get an error. Why? Because now, sorry. So where's the line 20? Line 20. So it takes a, not just a reference, it takes a mutable reference. So we should send a mutable reference. Oh, over here also. Mutable reference. What is it? In line 33. This is a line 33. Oh, what am I doing? So let's change it to a, mutable. Mutable I32. And let's take a reference of mutable again. Now everything is or should be fine. Now what? Now what's the error? So it says this is not mutable, so you cannot take a mutable reference to it. So let's make it mutable. All right. Let's make both of them mutable. Now everything works fine. At the end, we destroy it. 565. This is what we get. Well, I wanted to take this mutable. Why I wanted to take this mutable? Because, well, I just wanted to free it over here. So what I can do from this mutable is, since these are numbers, I can just make them, uh, something like 0. So I can make it like pre-initialized back to 0. I can do that, but why would I? So let's move. Yeah, that would be better. Now mutability. So we know that we have allow dead code, allow clone and copy. We have a structure that is book, and inside that we have author, title, and year. Author and title are static string, so it lives for the whole lifetime of the program. And we have a borrow book function. What it does is it takes a reference of the type book, this book, in a small book, and it says print, and it tries printing book's title and book's year, which is a static string. So yeah, it will do that. No problem. I immutably borrowed book's title, like whatever the book title would be in the main, and book's author. Sorry, book's year. Book's year, well, it might be just a copy, but since we are taking the whole reference to this book, well, no need to copy this book.here. We are not destructuring it. Then we have a new addition function that takes the mutable book, and we, change the books year to 2014. Since whatever it was, we change it to 2014 and we try printing it again. This function takes a reference to the mutable book and changes the year to 2014. Exactly. Now inside main, we say there is an immutable book, which is a book. And then we say the author is Douglas Hofstadter and the title is Glober Escher Back Gödel. All right. Gödel Escher Back. Year is 1979. So this is now stored in immutable book. Immutabook, not immutable, but immutabook. All right. Then we change this immutabook to a mutable book, by passing mute over here. So now this is an immutable book. After that, we have borrow book function, which borrows the book, and it is taking a reference to the immutable book, which is this. Won't this create a error? This creates error, I guess. Then we are trying to borrow a mutable book. This shouldn't be creating much of an error. I don't have any reason. New addition is like we are creating new addition for mutabook. We are immutabook. Now I don't think we should see some errors. Yeah, we see some well statements. Now let's try borrowing book from immutabook. Still works. So this still works. I thought this was some sort of error. Why? Because we are assigning immutable, which is a book book structure to here. So I think that this ownership of this immutable will be moved to this mutable, and this will become invalid. And that's why I thought that this would be an error. But what's really happening is, since these are static string, I think they are just getting copied to this mutabook or cloned. That's what I think. So therefore, both immutabook and mutabook lives. If I think these flags were to just vanish, I think that would create a problem. Yeah, see. So value of immutable book has been moved here, so we cannot use this. And this would not create any error. Exactly. So that's what I think. But what happened here was a trick. There was these flags. And these flags, cloned or copy the structure, which is book. That's why we didn't see much of an error. So this is great because the immutable book has been copied and cloned to mutable, so both can be accessed anywhere. Then in new addition, we try to change, take a mutable reference of mutable book. But if we try to do this new addition where we are trying to give it a mutable reference of immutable, since it is immutable, we can do this. But if we somehow make this mutable, somehow can we just say mute and that's it. Now this won't do any sort of error. No errors at all. See, but since it is not mutable because it is immutable, we get error. So we now know what this line was there for, and we shall move on. It is also telling us to see the static. So let's see the static, which is, we know it lives for the whole lifetime of the program. It is also in Rust, for example. So it'll come later on. So this thing will come later on in the same module print, like in the same 15th module, in the lifetime subtopic. Inside that we have 9 subtopics. Now that is irritating. Like having 9 subtopics in just one subtopic of it. All right, so mutability is done. I think we shall move on. We are back at aliasing. I think I have studied aliasing earlier also. Why is that? I think so. Aliasing. I don't see where the aliasing is used, because what I know is like we have created something like aliasing of i32 as this and all that. U8 is something like that. We have aliased our data structures back in this Rust, by example. I don't remember where, but we did it. But I don't see those keywords over here. So let's see what it's doing. So data can be immutably borrowed or any number of times, but when immutably borrowed, the original data cannot be mutably borrowed. Yeah, immutably immutable borrowing and mutable borrowing cannot happen simultaneously. Either you can have many immutable borrows or just one mutable borrow. This is the rule. Otherwise, there can be a data race and all that. We know the reasons. Why? Because we have a, I don't know, 100 challenge. So in that, we have a chapter regarding that. On the other hand, only one mutable borrow is allowed at a time. The original data can be borrowed again only after the mutable reference has been used for the last time. So it says, on the other hand, only one mutable borrow is allowed at a time. Why? Because original data can be borrowed again only after the mutable reference has been used for the last time. Otherwise, let's say there's someone who's taking that data and using it, and there is someone who is editing that data. So let's say there is a red wall, and you're seeing that red wall and taking that reference of red wall and saying, yeah, I have read. You're seeing that again, you're saying, I have read. And you're just taking a immutable borrow of that wall. That's an example. All right. And you're seeing that wall, you're saying it is red. You're seeing again, it is red. And somehow, someone who has a mutable reference to it just changes the color from red to green. And the next time you see that wall, you see green. And you freak out that how can this wall be green? I just saw it a millisecond ago and it was red. So that is something called data race. All right. So this will create some problem. So that's why Rust does not allow that. And let's see the code. So we have a structure which is point, and we have a x defined into it, which is i32, y, which is i32, and z, which is again i32 type. So colon and whatever written afterward is a type defined for it. Now inside this main, what we are doing is, first of all, we are creating a mutable point, and then we are assigning it a structure which is defined as point, and then in structure we are assigning the x, y, and z values as 0. Then what we are doing is, let a borrowed point, like we are taking a reference of this mutable borrow, but only a immutable reference. All right, this is not a mutable reference. Why? Because there's no mute written over here. We are not writing mute over here like this. This is an immutable reference. We can do this. This is allowed. We can take as many immutable reference as we want because we are only reading this data. Think about it in another example. Like you were going to a library, you were reading a book. You were taking that reference from that book, let's say some data. Let's say some scientist who was born in 1979. And somebody else also goes to that library for the same book. He can also read and reference to the same data, which is 1979. But think about someone who has a mutable reference to that book, who can change that book, who can write data to it. He goes to that book and erases the 1979, makes it something like 2000. And now when you go back to that reference where you want to see what is the data, instead of seeing 1979, you see 2000. Now that creates the error. But you can have as many as reader, but no writer. Like you can have many immutable reference to that book, which will just go there and read 1979, do nothing to it, come back. You can have as many as reference to that book now. But as soon as you make a mutable reference, no, that cannot happen simultaneously. Either just have a one mutable reference or, many immutable reference, not both simultaneously. That's the rule. Now data can be accessed via the reference and original owner. So there is a println and we are trying to print a borrowed point dot x, another point from here, another point dot phi, and pointer point from here is point dot z. We can do this. No error. Error is can't borrow point as mutable because it is currently borrowed. So if you try to do this, try a mutable reference to that point, mutable borrow, you cannot do this simultaneously. You would have to, remove these two lines and then you can do this. Then what we are trying to do is the borrowed values are used again here, after mutably borrowing it. This will become invalid. You cannot do this simultaneously. All right. But right now, since I'm not uncommenting this, this is valid. This is valid. All right. Shall we try printing it? But we have other codes too. So we might get an error. So let's read the whole uncommented thing first aloud. Now the immutable reference are no longer used for the rest of the code, so it's possible to reborrow with a mutable reference. Yeah. So now immutable, since it said that now we are not using this immutable reference again, so now we can take a mutable reference back, because as soon as we used immutable reference over here, we'll get an error that we cannot mutate it. But since we are not doing that, we can first of all take a mutable reference to it and change it, and then take an immutable reference to the new data. That's what we can do, but not like this. All right, now we change the mutable borrow x to a 5, y to 2, and z to 1. Now we try to do something like mutable borrow, and whatever the x and y and z value is, we try printing it, and we can do that. Now we are taking the reference to the point, which is new borrowed point, and we can do this. We'll get a new data. That's it. Let's try printing it. First we'll get 0, 0, 0, and after this point we'll get 5 to 1. 5 to 1. All right. Now there are many error points, like since this immutable reference is there, we cannot take a mutable reference. This will give us an error. Let's see. This gave us error, cannot borrow point. All right, we know that. So now we uncomment this. So it says error cannot borrow point as a mutable because it's currently borrowed as immutable. We cannot do this. All right, so we now know what this is used for. And over here it works because we are not taking this, we are just leaving this immutable reference alone. Like we are not using it again ever in this code. This automatically sort of gets dropped by Rust. All right, we are not doing it. But if we try accessing it, accessing this line after mutably pointing it, it will give us the same error that we were getting over here. But that's not what we are trying to achieve. So you want to change the value, we'll not use these values, we'll not use these variables. We'll just give it a new variable with a mutable pointer, mutable reference to the point, and then we'll change the point, and now we can access these values easily. But now it is telling us that we want some errors. So let's see what sort of errors we can get. It says cannot borrow point as immutable because it is currently borrowed as mutable. So now over here it is trying to borrow it as immutable reference. It can take a mutable reference to it, no problem at all. Oh, there's a problem to it. But we cannot take a reference to mutable or any sort of reference after that. No two mutable reference can be there. Why not? Because, well, if there are two mutable reference, like two person writing the same book but with different data, like 1979 one person came with a mutable reference, he wrote something like 2000, and the person two sort of came writing into the same data, same book, but a different data. All right, so he sort of wrote something like 2010. Now we have two data. Whom should we believe? We can't share two mutable reference simultaneously. We can do this after this mutable reference sort of not being used. Like this we can use it. Oh, first of all, let's we can do this because now we are not using any sort of mutable variable. Like if we were not to do any sort of stupid things, we can do something like this. Since now the earlier mutable reference has ended, we can take another mutable reference. That's what we can do. Because the earlier mutable reference which was there, which is this, has ended over here. It is not used again down the line. So we can take a new mutable reference. But we cannot do this over here. Why? Because it already has a mutable reference. We cannot have two mutable reference or any mutable reference and immutable reference at the same time. If we try doing it, it's no error. All right, we get a no error. And if we try printing y, we'll be able to print y easily, very easily. Print, what do I want to print? I want to print y. Oh, inside a semicolon. Let's do this. Let's try printing y, and no errors should be there. So I think, yeah, we see y is 2. Now I think there shouldn't be much of an error. If we say, well, y, it should become something like 6. It will become 6. It will not become, oh, sorry. Semicolon, 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 colon. Now what? It says expected ampersand mutable I32, which is we defined mutable borrow and dot x. So we said mutable borrow of point dot y only, and we are changing that y to 6. All right. I don't know what the error is, but we are just taking y and we are trying to change the y. I think we can do this, but it's telling me we can't. And what is the error? It says mismatch type. It says expected something like ampersand mutable I32, but it sort of found an integer. How about I make it ampersand? And then I say mutable, which is stupid, but let's go. Let's go with it. Now what? Cannot assign twice. First assignment happens over here, where we are changing y to something. We are assigning point y to this. Now cannot assign twice to immutable variable. It says oh shit. That's what the error was. We don't want this, I think. Oh shit. We have to dereference the y because it is a pointer. So, yeah. Now this will. Yes. Sorry. And if we don't do this, we'll just error 2, which has been there. Yeah, error 2. But if we want to change this value again, we can do this. Yeah, see this? We can. I think we can move on with aliasing the ref pattern, and I think this is the end of it. Yeah, this is the end of it. Since lifetime is very long, we'll not be able to cover it up today, so we'll see that tomorrow. Now this, we have again derived copy and clone. So we can use point, we can assign point to an immutable variable, and we can assign that immutable variable to another sort of immutable variable. No problem at all, because we are copying it or cloning it. So yeah. So in point, x is I32, y is I32, and then main, we are trying to do something. But before that, let's read the theory. It's telling me something like when doing pattern matching or destructuring via let binding, the ref keyword can be used to take a reference to the field of a structure or tuple. The example shows a few instances where this can be used. This can be useful. All right. So we have a C which has a character of Q. C has a character of Q. I don't know why, but yeah, that's what it is. And then there is a reference of ref C1. We are calling a variable ref C1, which is taking a reference of what? Of C. So this is a reference. We can do it like this. Or we can just directly, instead of just passing C, we can pass out directly a reference of C. We don't have to mention that this is a reference of C. So we don't have to, define ref over here because we are already passing a reference of C. So let's read the comment. A reference borrows on the left side of an assignment is equivalent to just an ampersand borrow on the right side of the assignment. So either we can do this sort of ampersand on the right side, or we can do a ref on the left side. This is same. This is just taking the reference of C, which is the pointer towards the character, which is Q. Now what we are trying to print something like, the destructuring, or sorry, going back to reference of C1, the value, and we are not we are not equating between uh, pointers. We are not saying pointer 1 is equal to pointer 2. All right, we are not comparing between pointers. We are comparing the values, which is same in both the pointers, which is q. So this should give us a true. So we'll get a true. All right, because both have a reference of q character. And then we have a pointer. We have a point which is of structure of point. X and y has a value of 0. We are trying to copy. We have a copy of x, and since we are not using it, therefore we are just creating an underscore. The reference is also valid when destructuring a struct. All right, so x, for x we are taking a reference of ref to x. As for y, we are not doing anything. A wildcard is there, whatever it is equals to point. So now we are destructuring the point which is defined over here. We're destructuring this point to this bigger point, and instead of taking x and y, we are just taking a reference of x. As for y, whatever it is, just give it. And then what we are trying to do, we are trying to return since this is a sort of scope, we are trying to first of all return whatever the value of x is to the copy of x over here. So we are returning the reference of x to a copy of x variable. So this will give us this a value of 0. Let's move on to next one, which is a mutable copy of a point. So this is a mutable copy, not a reference, but a mutable reference. All right, which means it can change the value. So what we are doing in a scope is we are destructuring with a bigger point, and we are taking a mutable point, which is just point, but over here. So ownership of point has changed to a mutable point, or has been cloned or copied, because that's what happened. All right. And then what we are doing is we are taking a reference which is mutable reference of y, which indirectly means ampersand and mute. This is what it means. All right. We are taking ampersand mute of this y. Either we can do this over here, or we are directly doing it over here. And then x is whatever, whatever the x is, give it directly. We don't need to change x for any reasons. And then we are trying to mutate whatever the y we got from here to 1 instead of 0. So now this mutable point in this scope, well, y became sort of 1. Then we are trying to print x and y. Since it is getting out of this scope, whatever you're trying to mutate will either remain over here or will just get changed. Since we are changing a mutable reference over here to mutable point, so y will become 1. So if we try to print y, it will become 1. And mutable point, mutable point dot y becomes 1. I guess, yeah, something like that, because both of them are not same. This mutable point is sort of a copy or clone of this point, not y. So I think this will become 1, and this will remain 0, 0. Then what? Then we have a mutable tuple, 5 and 3. One is a pointer, one is directly a number. All right. So mutable tuple is consisting of sort of a pointer and then a tuple. And what we are trying to do is mutable tuple that includes a pointer. Yeah, this is a pointer. And what we are trying to do in a inner scope is we are destructuring the mutable tuple, which is this, and to change the value of the last. Last is just a number, and we are trying to change the value of it. So let whatever this variable is, and the first one, which is a pointer, let it remain like it is. And the second one is, now we are taking it a reference mutable of the last. And then we are we were destructuring the mutable tuple. That's what we did. We took the last element and take a reference which was mutable. And then for the last, we, instead of making it 2, we made it from 3, we made it to 2. And then we are trying to print it. All right, everything works. we see some error. We'll not see some errors. So this is 5 2 as expected. 3 has changed to 2. So I think we are done with this. So how about, we just remove it. And now we have something new, which is mutable point. We'll see this. So point was, point x and y is 0 0, and then from mutable y, I know we changed it to 1, so that's why we get a 1, exactly as we expected. As for this one, we did not printed the copy of x. We can do that, but all right, let's do it. For now, let's first of all see this, which is true. So this is also true, so I think we can move on from there also. Now this is just the remaining thing. If we just try to print the copy of x, we should get something interesting. print print. Oh, then we are trying to print a copy of and x. Just remove this underscore because this is not an unused variable now. This is a used variable. I missed a semicolon, but doesn't matter. It says expected function found a macro. Oh shit. Yeah. So we get a 0, which is the value of x. All right. This is also what we expected. So I guess we finished this ref pattern. It was interesting. It was filled with, well, yeah. So you just need a presence of mind, and this is a very simple, not very simple, but yeah, a simple code. We just need to, approach this code very stepwise. If that's what happens. If you leave any sort of step, you will get confused and might get some sort of errors. Now, next was lifetimes. I guess we'll see this tomorrow because we don't have much of a time. Functions. Like, this is a topic in itself. Methods. Starts.